start by looking at the rules of heat. Then we'll see exactly how gases change shape. And finally, we'll bring it all together with the ultimate gas equation. So, part 1, the rules of heat, or as it's officially known in physics, thermodynamics. Let's start at the very beginning with the Zeroth Law. It's really just a simple piece of logic. It states that if two separate objects are perfectly balanced in heat with a third object, well, they've got to be perfectly balanced with each other too. This idea is literally what defines temperature. It's exactly how that thermometer in your medicine cabinet actually works to see if you have a fever. Think of it like this. If body A is the exact same temperature as body C, and body B matches C as well, then naturally A and B have to match each other. They're sharing perfect thermal equilibrium. Moving right along to the first law of thermodynamics. You probably know this one as the conservation of energy. It's the ultimate cosmic rule that energy is never just created out of thin air, and it's never truly destroyed. It simply transforms, or it hops from one place to another. Picture a perfectly closed box. When heat, which scientists call Q, enters this box, the internal energy inside has to go up, and then that energy can leave by doing actual work on the outside world. It's a perfect balance. The total change in energy is just the heat added minus the work done. You see, the energy always goes somewhere. Now, the second law is all about direction. In nature, heat always flows from something hot to something cold. It literally never happens the other way around on its own. This rule also introduces us to entropy, which is really just a fancy word for disorder. And in our universe, natural things are always moving toward more and more disorder. So if you put a hot object right next to a cold one, the heat naturally rushes straight across to the cold side. That spontaneous movement, it's a one-way street. It only goes one way, kind of like time itself. And that brings us to the third law, which takes us to the absolute coldest place imaginable, absolute zero. It basically says that if you could somehow cool a perfect crystal all the way down to absolute zero, its entropy, its disorder, would completely stop and hit zero too. Now, reaching absolute zero is practically impossible in real life, but it gives us this beautiful, completely still baseline to work from. Okay, moving on to part 2, let's look at exactly how gases change shape with the famous gas laws. Our first stop here is Boyle's law. It tells us that if you keep the temperature perfectly steady, a gas's pressure and its volume are basically playing on a seesaw. They're inversely proportional. Think about squeezing a balloon. You make the volume smaller, so the pressure inside shoots up until, pop, it bursts. You can see the math play out here. A tiny volume of 1 gives us a really high pressure of 6. But as we let that gas expand to a volume of 3, the pressure drops down to 2. You squeeze it, pressure rises. You let it expand, pressure falls. It forms this very gentle, predictable curve. Next up, we have Charles's law. This time, if you keep the pressure steady, volume and temperature are directly proportional. Heating a gas simply makes it expand. It's the exact reason hot air balloons inflate and fly when you hit the burner. The extra heat literally forces the gas to take up way more space. Just look at how these numbers grow together. Down at a chilly 200 Kelvin, the volume is pretty small, just 1. But as we crank the heat up to 400 Kelvin, the volume scales up perfectly to 5. So cold gas is compact, while hot gas really wants to expand. Now, I want you to imagine your gas is trapped inside a totally rigid metal container that absolutely cannot expand. This brings us to Gay-Lussac's law. Since the volume is locked in place, heating the gas has nowhere else to go but into pressure. So pressure and temperature become directly proportional. See how as the temperature doubles from 200 to 400, the pressure climbs right alongside it, going from 1 to 5? At low temperatures, it's pretty calm inside that container. But when you crank up the heat, those molecules start moving furiously, smashing against the walls and spiking the pressure. It's exactly why you never, ever throw a sealed aerosol can into a fire. All right, part 3, the ultimate gas equation. This is where we bring everything together. But first, we have to talk about the sheer amount of gas, and that's Avogadro's law. It says that if your temperature and pressure are constant, equal volumes of any gases will hold the exact same number of molecules. In science, we measure this amount in moles. So very simply, more moles of gas will take up more space. It's a perfect match. If you have 1 mole of gas, it takes up a volume of 2. Pump in more gas to reach 3 moles, and the volume scales straight up to 6. It's a completely direct relationship. So what happens if we start mixing different gases together in one container? Well, Dalton's law of partial pressures sorts that out. It basically says that each separate gas inside that container acts as if it's completely alone. They just don't bother each other. It's actually super straightforward. You just take the pressure of gas A, add the pressure of gas B, and then add gas C. Put them all together and they equal your total pressure. Each individual gas is just contributing its own distinct piece to the grand total. And finally, the moment we've been building toward, the ideal gas law. This is the master formula. It beautifully bundles up Boyle's law for pressure and volume, Charles's law for temperature, and Avogadro's law for moles into one amazingly elegant equation, PV equals nRT. This really brings the whole explainer full circle. From the strict conservation of energy, right through to the inverse relationship of squeezing a balloon, all the way to this unifying ideal gas law. It shows us how perfectly connected everything is and how beautifully things balance out in the physical world. Before we sign off, I want to leave you with something to chew on. If the third law tells us that reaching absolute zero is practically impossible, does that mean the disorder and entropy of our universe are just destined to increase forever?